Right, this capacitor is initially uncharged. Immediately after the switch closes, the capacitor voltage is which of these? And here it's almost a trick question. Since the capacitor is uncharged, the voltage on it is 0. Because, of course, we remember that the voltage on a capacitor is the charge on the capacitor divided by the capacitance. And right after you throw the switch, the capacitor remains uncharged. So we end up with this. All right, consider this circuit with no charge on the capacitor. It is hooked up, obviously, to an EMF source, and there's a resistor as well. What happens when the switch is closed? Take a couple minutes to think about it, and what would the response be? What's going to go on? Describe what happens next. Well, we can apply Kirchhoff's laws. What happens, of course, is that once the circuit is closed, the positive charge on the battery has a conducting path or has somewhere to go, so it goes down here and it gets stored on this capacitor. As it runs through the resistor, dissipating power or whatever, lands on the capacitor, kicks out some other positive charge that completes the circuit, and so stuff flows, and that will keep going until, of course, eventually the capacitor is fully charged and its voltage exactly balances the battery's voltage. Applying Kirchhoff's laws, we know that every dq that moves through the resistor is added to the capacitor, to the positive plate. So dq is just d capital Q. We have Kirchhoff's law says we start here, we go up and gain the battery voltage, we lose the resistor's voltage, we now lose the capacitor's voltage because we know that it's going to charge this way. So as we move around this circuit, we're going against, right? We're going against the voltage. The voltage drops across the capacitor. So we get two minus signs. And then we know that capital I is just dq dt, and Vc is just q over c. So we get this differential equation. This is now an ordinary first-order differential equation, but it's inhomogeneous because it has this term here. All right, it has a not function. It has a constant term that is not itself a function of our variable q. Just clean this up again. Here's our differential equation that came out of Kirchhoff's laws. And we'll say when fully charged, the capacitor will hold a maximum charge that is its capacitance times the voltage that will be on it, which is the EMF. So the maximum charge in the capacitor is C times E. I'm now going to propose the following Ansatz. Ansatz is a fancy German word for answer. It's a technique where you say, I kind of know what's going to happen, and I'm going to put it in and see what that implies. So I'm going to assume that what happens here is that the final charge is, or the charge at any given time, is going to grow exponentially, and it's going to look something like the final charge minus some exponential bit that will go off to 0. So at the start, this is 1, and the initial charge is 0. And when t becomes essentially infinite, this becomes 0, and the final charge is just the final charge. The purpose of doing ansatz is we then plug and chug and see what happens to the solution. So here's our ansatz, and here is our equation. We take the derivative because we'll need it, and we get this stuff. So we get that the derivative, which is, remember, the current, is q max over tau, e minus t over tau. And we put those in where they're supposed to go. And then we do some just grungy algebra. We just kind of grind it out and just keep doing this stuff. And if you do everything very carefully, you'll find that all 4 of these terms end up canceling, and 0 equals 0. So we have proven that this is, in fact, a solution to this differential equation. And since it's first order, it's the only solution. All right, putting this together, it means that the solution now is that the charge is some maximum charge times this growing exponential. Actually, this limited exponential, but this means the capacitor charges with the same time constant as it discharges, or at least has the same form. Very often in circuits that you build, the resistor will be different. So that you might have, for instance, a slow charge where you don't have to deliver a lot of current, and then a fast discharge so you can get a lot of energy out all at once. This is, for instance, when you turn on flash cameras and so on, or defibrillators for heart attack victims. You might have noticed, like, on medical dramas where you have this, like, really long, they say, get ready, clear, turn on thing, and here it goes, and then it discharges really fast because they've swapped in different resistors by throwing the switch. But the key thing coming out, the time constant for the circuit looks the same. It's just R times C. In this case, the charging graph is upside down, quote unquote, compared to what we had before. we see that we start with no charge and we grow, but it exponentially levels out and asymptotes over to Q max. And we can see after one time constant, we have 1 minus 1 over E. And after two time constants, we have 1 minus 1 over E squared. And very rapidly, we get to basically 1. So consider this. The red curve shows how the capacitor charges after the switch is closed at t equals 0. So that's this one. Which curve shows capacitor charging if the value of the resistor were decreased? All right, our first thing is, if we change the resistor but we don't change the battery, then the maximum charge will be the same, because Q is still going to be C times that battery, and it hasn't changed. So we have to end up in the same place, which means it has to be either B or C. A has overshot and brought too much charge, and D is clearly going to asymptote too slowly and never reach the original maximum charge. And then the question is, should it be a quicker charge or a slower charge? But if we've decreased the resistor, we've decreased the time constant, meaning it charges more quickly, because the time constant is how many times we have to wait until it gets charged. So our answer should be B.